I'm Mahershala Labao, and I'm going to introduce to you the significance and purpose. Corrosion is not just a chemical process. It is a serious economic safety and environment problem worldwide. Its significance can be introduced to several aspects. Number one, economic impact. Corrosion has to billions of dollars in losses annually from repair, replacement, downtime, and maintenance. For example, industries like oil and gas, shipping, construction, and transportation spend daily on combating corrosion. Preventing corrosion reduces long-term operational costs. Number two, structural safety and reliability. Corrosion weakens the load-bearing capacity of bridges, buildings, and aircraft, pipelines, and ships. This can result in catastrophic failures, collapse, leaks, or explosion. Prevention ensures the safety and reliability of a critical infrastructure. Number three, reduce conservation. Metal like steel, aluminum, and copper are required every intensive mining and processing. Corrosion causes premature replacement, wasting natural resources. Prevention expanded service life, reducing demand for raw materials. 4. Environmental protection. Corrosion of chemical tanks or pipe can cause leaks for soil, river, and oceans. Preventing corrosion safeguard our ecosystem and public health. Number 5. Operational efficiency. Is industrial plants corroded equipment leads to leak, contamination, and produce stoppages. Proper control ensures smooth and interruption operation. Next, the purpose. The purpose goes beyond stopping rust. It aims to minimize, and delay corrosion effectively. Number 1. Service life of materials. By applying protective coating, using corrosion-resistant alloys, or applying coated protection, metal lasts much longer. This maximizes the return to invest for infrastructure and machinery. Number 2. Ensures safety and reliability. Corrosion prevention avoids accidents like oil spills, structure collapse, and aircraft part failures. Protect both human lives and property. Number 3. Cost savings. Preventing measures, coating inhibitor, inspections are cheaper than constant repair or replacement. Industries adopt preventive maintenance as part of assets management. Number 4. Support sustainability goals. Reducing corrosion means conserving energy and natural resources. It helps industries align with sustainability or sustainable development and environmental protection standards. Last, compliance and standards and regulation. Government organizations safety codes require corrosion prevention. Example in construction, oil pipeline, and invasion. Prevention ensures and compliance and avoid legal liabilities. In short, insignificance lies in the massive impact corrosion has on safety, cost, and environment, while for the purpose is to protect infrastructure, conserve resources, and ensure safety and maintenance efficiency.
Hello everyone, my name is Christian Halasan, and my report is all about electrochemical nature of aqueous corrosion. Aqueous corrosion in aqueous environment like water, moisture, or humid air is fundamentally an electrochemical process, which means it involves the transfer of electrons through coupled oxidation and reduction reactions on metal surface. Here's the breakdown. Number 1. Formation of anodic and cathodic sites. A metal surface is not perfectly uniform due to impurities, stresses, or surface roughness. Different areas behave differently. Anodic site. Here, metal atoms lose electrons or oxidation. Sample for iron or Fe is equals to Fe2 plus 2E. This is the starting point of rust formation. Cathodic site. The released electrons travel to another area of the metal where reduction reaction occurs. Common reaction in neutral or alkaline water. Oxygen reduction, O2 plus 2H2O plus 4E4OH. So corrosion is essentially a tiny galvanic cell forming the surface of the metal. Number 2. Role of electrolyte or water with dissolved ions. Pure water itself is a poor conductor, but in reality it contains dissolved oxygen, salts, and carbon dioxide, which make it conductive. This electrolyte allows ions and electrons to move, completing the corrosion circuit. Example, like seawater is highly corrosive because chloride ions or Ci makes it an excellent electrolyte. Number 3, all-over corrosion reaction. Combining the anodic and cathodic half reactions gives the overall corrosion process. For iron in neutral water with oxygen. Anode, Fe is equals to F2 plus 2E. Cathode, O2 plus 2H2O plus 4E is equals to 40H. Overall, 2Fe plus O2 plus 2H2O plus 2Fe, which rather oxidize rust. And number 4, factors affecting the electrochemical process. Oxygen availability. More oxygen accelerates cathodic reactions. pH of solution. Acidic conditions like low pH, high hydrogen. Increased corrosion since hydrogen reduction for 2H plus 2E equals to H2 is favored. Temperature. Higher temperature speeds up electrochemical reactions. pH of solution. Acidic conditions with low HP or high hydrogen. Increased corrosion since H1 reduction is 2H plus 2E, H2 is favored. Temperature. Higher temperature speeds up electrochemical reactions. Presence of salts. Chlorides and sulfates enhance conductivity and destroy protective oxide films. Number 5. Importance in prevention and control. Understanding this electrochemical nature is the key to developing corrosion prevention methods like coating, paint, galvanizing, block electrolyte and oxygen from contacting the metal. Cathodic protection. Attach a more active metal like sacrificial anode so it corrodes instead of the protected structure. Corrosion inhibitors. Add chemicals to water that slow either the anodic or cathodic reaction. Material selection. Use metals, alloys that naturally form protective oxide films like aluminum, stainless, and stainless steel. In summary, aqueous corrosion is basically the result of a microscopic electrochemical cell forming on the metal surface, where one part acts as anode metal dissolution and another cathode reduction reaction. The presence of water and dissolved ions sustains this process, adding a gradual metal deterioration.
Corrosion rate determinants. The rate of corrosion, how fast a metal deteriorates, depends on multiple interacting factors. Understanding these determinants is essential in designing materials, selecting environments, and applying proper prevention strategies. Number 1. Nature of metal. Position in the electrochemical series. Metals high in the activity series like magnesium, zinc, aluminum corrode faster than noble metals like gold, platinum, silver. Preservation. Some metals, example aluminum, stainless steel, titanium, naturally form thin, stable oxide films that slows corrosion. Purity and alloying. Impurities can form tiny galvanic cells, increasing corrosion. Alloying can either increase resistance, example stainless steel with chromium, or reduce it if poorly balanced. And 2. Environmental condition. Moisture availability. Corrosion accelerates in humid or wet environments compared to dry conditions. Temperature. Higher temperature generally increase reaction rates and the aggressiveness of electrolytes. Pollutant. Industrial gases like sulfur dioxide, carbon dioxide, and hydrogen sulfide dissolve in moisture to form acids, making corrosion worse. Oxygen concentration. Oxygen is needed for the cathodic reaction. More oxygen often increases corrosion but uneven distribution. Low oxygen under herbicides causes localized attack. And number 3, electrolyte properties. Conductivity. Electrolyte rich in salt like sodium chloride in seawaters conduct ions, better accelerating corrosion. pH level. Acidic environment, low pH, promote faster corrosion, especially hydrogen evolution. Alkaline condition. sometimes promote protective oxide films, ion content. Chlorides break down protective films, leading to pitting corrosion. Carbonates and sulfates can form protective scales in some cases. 4. Surface condition of the metal. Rough versus smooth surfaces. Rough or scratched surface corrode faster due to more active sites. Coatings. Painted, plated, or anodized surface resist corrosion if intact, but damaged coatings may cause localized attack. Residual stresses. Metals with stress, from welding, rolling, bending, are more prone to stress corrosion cracking. 5. Design and geometry of structures. Crevices and corners trap moisture, and debris, creating differential aeration cells that accelerate corrosion. Water stagnation. Areas where waters or electrolyte does not flow freely corrode faster. Galvanic contact. If two dissimilar metals are joined, galvanic corrosion occurs, with the more active metal corroding faster. 6. Time of exposure. Corrosion is cumulative. The longer a metal is exposed, the more damage occurs. However, in some cases, corrosion slows down over time if stable protective layers forms. Example, patina on copper, oxide on aluminum. Why understanding corrosion rate matters? Engineer calculate corrosion rate. Example, millimeters per year or milliliters per year to predict service life of equipment. Knowing the rate helps in choosing the right materials, coatings, or protection methods for a specific environment. For example, a steel bridge in a marine environment will corrode much faster than in a dry inland area, requiring stronger prevention measures. In summary, the corrosion rate is controlled by the metal's properties, the environment it's in, the nature of the electrolyte, and the design surface condition of the structure. Prevention strategies must target these factors to slow down or stop corrosion.